That you had a good break and now you are more energetic to start learning new topic. So there is actually two topics left from this chapter, and it will be finalized by this Friday. Then we will decide about when having the exam for this chapter. Okay, we can discuss it at the end. Okay, so what I am teaching now is related, so you need to learn about this in order to be able to understand what is coming, which is of course very important. It's called optimization. It will be on Friday. Okay, so here we have talked so far about finding extreme values of functions. Yes, for example, maximum of a function, minimum of a function. But in those cases, we didn't care about absolute maximum and minimum of the function. Yes. So if you remember, for example, we had something like this. So here we consider this a local extreme, a local maximum point, because it is higher than the points in the vicinity of that point. Okay. But of course, in this graph, it is clear that the height of this point is, for example, is less than the height of this point. So compared to this new point, the previous point, even though it is a local maximum point, is not the absolute maximum or the maximum of the function. So today we want to talk about these things, and we restrict ourselves to the intervals. Okay, there are two points about that, because usually if you don't restrict yourself to some kind of interval, usually functions goes forever here and there, so there is no meaning of talking about absolute minimum and absolute maximum. Okay, because it goes up forever, so you would say that there is no maximum for this, there is no upper bound for the function, and there is no lower bound because it continues forever from this direction. So this is one reason that we want to limit ourselves on some intervals. Okay, and the other point is that in reality, the functions that we are working with in real life, they have a limited domain usually. I don't know, for example, let me just write something and I will clean it up. For example, assume that this is the profit that you gain by selling, I don't know, a number of commodities that you produce, for example. So you produce, for example, shoes, and X is the number of shoes that you produce, and this profit, this P is the profit that you gain after selling X units of those commodities. Okay. So here, for example, it is completely clear I cannot work with negative values for X, because it is completely meaningless to have -5 shirts or -10 shoes. Yes. So for example, this means that I cannot consider the values, the negative values for X. Or even we cannot consider that X can be infinitely large. It is not sensible to ask what is the profit if I can produce infinitely many shoes. Okay, so you have an upper bound for how much you can produce based on the equipment that you have or whatever. So for example, I would say that, okay, if I start producing shirts between zero number of shirts up to, for example, I don't know, it depends to your capacity of the factory or whatever, for example 1,000 per day, then how much maximally I can gain? Okay, so this is a sensible question. But if you say that, okay, there is no limitation for X, it's not realistic. Mathematically it's okay, you can talk about those things, but if you want to use mathematics to solve a practical problem in real life, then of course you need to limit yourself to some interval. So this is from practical point of view, and even from mathematical point of view, usually if you do not put a limitation, usually, not always of course, if you do not put a limit on that interval, the function usually goes very high or very down. This is usually, for example, an immediate counterexample is the sine function, for example. For example, a sine function continues forever, but it doesn't go higher than 1, it doesn't go lower than -1. So of course there are exceptions, but in general this is the case. Now today we want to talk about finding maximum and minimum of a function, okay, of course continuous function only, on a given interval. Okay, so let me first of all, let me make clear, everyone have the same understanding as mine about an interval. When I say an interval, there are many different intervals. So interval, it means geometrically, it means that you have this is your real line, the line of numbers, for example. Okay, an interval means that take one piece of this line. Okay, so for example, I can take this piece. This is an interval here, this blue one. Okay, or I can say that, okay, I will take this piece from here onwards up to infinity. This is one piece. Okay, and then it depends. Sometimes I include the endpoints, I show them by a filled dot as usual. Sometimes I exclude both or one of the endpoints. Then I will show it with a hollow circle. It means that I am conveying this idea that, okay, this endpoint is excluded. So in general, geometrically, an interval means one piece. It doesn't matter is it long or short or whatever, one piece of the real line. That is the meaning of an interval. Intervals like this are called unbounded intervals because they are, of course, they are bounded from one point, but they are not bounded from above. They can continue forever. I can assume that I have an interval of this form. It starts somewhere, it doesn't go up, but it goes indefinitely to the negative value. So this is not bounded from below, it is bounded from above. This one is both bounded from the below and bounded from above. We just usually say it is a bounded interval. Okay, the intervals that you are interested in this lesson are bounded intervals. It means that you have a lower bound and an upper bound. Okay, so that's the meaning of interval. So let me just clean this, we don't need it anymore. But mathematically, bounded intervals fall into 4 categories, yes? So we can have an interval like this, a less than or equal to x less than or equal to b. We can have an interval like this, a less than x less than b. We can have an interval like this. Let me give a little bit more space. And then I can have an interval like this, including the left point and excluding the right point, or the other way around. So these are the intervals of interest for us today. Okay, there is a name for that. It's called closed interval. I don't know, it is not in the book, but it is called closed interval. This is called open interval. And this is called semi-open, semi-closed. It doesn't matter how do you write it. For example, I write semi-closed. You can also say it's semi-open or open, yes? The same thing here. So this is also semi-closed or open. Okay, so remember, when I say closed, I mean I am including the endpoints. When I say open, it means that I am excluding both endpoints. Semi-closed or semi-open, it's not clear which one is included, which one is excluded. I need to be specific about that. And if I want to draw some diagram for this, for example, if this is the x-axis here, and if this point here is A, for example, if this point here is B, if I want to draw a picture for this, I have to include this point by putting a filled dot showing that I am respecting this inclusion, and then everything in between. So what you see in this green part, every green part that you see in this picture is representing this interval. This is a geometrical representation of this abstract interval. And then of course it is clear what will happen here. I have an interval here again, I have the x-axis here, and then one point here is probably A. So let me just denote that. So this is, for example, A, and this is B. But here I have to show that I know the topic. So let me make it clear. So I have to exclude these 2 points, but I will include whatever between these 2 points. Yes? And of course you can guess. Let me just draw one of them at least, so you can guess what will happen here. Yes, so here I have this point A, I have this point, for example, B, and then A is included, so it should be a filled dot. B is excluded, so it would be a hollow circle, and then whatever in between. Yes, so that's a representation of this interval. Okay, but now we want to limit ourselves to intervals, so I will not let the domain of the function goes below unboundedly, goes above unboundedly. I want to limit the domain of my function, and then I want to talk about maximum and minimum of those functions. First, let us consider closed intervals and continuous functions. So continuous function it means that I can draw the graph with one pen stroke, a continuous function on closed intervals. Okay, so let me emphasize here on the word closed and the word continuous. Okay, so this is the topic that right now I want to talk about. First of all, so let me draw some pictures for you. Okay, so here let me draw a coordinate system here. Yes, and then I have it here. And then, for example, let me limit myself to an interval. Let me, for example, give this point A. I want to make it filled point. I'm including these points. As I told you, I want to consider closed intervals. And then let me draw a function which is limited between these 2 intervals. Yes. So for example, let me draw this function. It goes here, and it goes there, and then it goes here, up to here. So for example, this is the graph of a function. If I ask you, is there any highest point on this graph, you immediately realize that yes, this point, first of all, it is included. It's a filled point, so I can point to it. If it was excluded, I cannot say this point is the highest point because it is excluded. But now, this is the highest point, and then you see that more or less here is the lowest point. So this is a continuous function. I can draw it with one pen stroke, and then you see that this point is the highest point and this point is the lowest point on the graph. So I would say that this height is the maximum of my function f, let me call this function f, on the closed interval between a and b. It means that if I limit my x values to be in this interval, then the highest point is this point and the lowest point is this point. We don't know what is the behavior of the function after that. Might be the function continues going up. Then if I increase the interval up to here, this is no longer a maximum because now maximum point is another point. But we don't care about what is happening outside the interval. Within this interval, this is the highest point and this is the lowest point. So let me be more specific here. So I would say that, for example, in this picture, this height is minimum and this height is actually a maximum. And now you see that minimum is also a local minimum here. No worries about that. This is not only a local minimum, but it is minimum. It is lower than any point in the vicinity. Of course, it is clear that this is also no. Sorry. It is clear that this is lowest point. So it means that this is also a local minimum. It is also lower than the points in the vicinity. So this value, how much is that? You need to calculate is the minimum of your function. Let me write the name of the function here. You say that, let me, for example, mention these numbers here. For example, let me write this length, assume that this is C, and let me assume that this length is D, and then I would say that maximum of my function f is equal to D, and minimum of my function f is equal to C on the closed interval between A and B. So this is the information that you get from this picture. Hopefully it is clear. Something that is important to understand, we will come up to. So you see that maximum happens at the end point, at one of these endpoints. Minimum happens at an interior point, yes? This is an interior point. This is happening here. So if I ask you where maximum happens, you say that at x equal to b. Let me write this information as well. So max occurs at the endpoint x equals to b. Minimum occurs at the internal point so for example, let me give this a name. Let me call it alpha, for example. What I want to convince you about is that this is always the case. Minimum and maximums of continuous functions on closed intervals can occur in two different categories of points. One, the endpoints, or a local extreme point. And I think just drawing some diagrams, you can immediately convince yourself that this is the case. Okay, so let me, for example, try to draw some diagrams here. Let me use this tool here. For example, in this case, minimum occurs in an internal point. It is within the interval, and maximum occurs at the right endpoint. You can imagine a graph like this. Okay? If the graph is like this, if I ask you where the maximum occurs, you see that maximum occurs at the left endpoint. This is the highest point, and minimum occurs at the right endpoint. So again, you see max and mean are happening at the endpoints, both of them in this case. Okay, I want to, is there any questions here? Please let me know, because when I take my pen, this will disappear. This is one possible case. One possible case was this green one. You can imagine this case. I can go from here and then I go up to here continuously. Again, max and mean are occurring at the end points, but this time minimum occurs at the left end point and maximum occurs at the right end point. Okay, I don't know, I can have this situation. I can go up and then come back here and then go up to here and then here. Okay, so if you see, if I ask you where the maximum occurs, maximum is this point, occurs here, which is the internal point. Minimum occurs here, which is again an internal point. Okay, so this is clear. Just playing around with a little bit of curves, hopefully you immediately convinced under two conditions. These two conditions cannot be relaxed. Under two conditions, continuity of my function and closedness of my interval, the max and mean of my function can occur in two categories of points. One possible candidate for the points of this kind are the endpoints. Another one are the local extreme points. Okay, is that understandable? Okay, so it seems that this is the moral that we can take. Max and mean of continuous functions on closed intervals can occur. Yeah, let me write occurs, just it's enough, occur at either endpoints of the interval or the internal local extreme points. Okay, so hopefully you are convinced about this by drawing some of these diagrams. But let me a little bit talk about why I emphasize on continuity and closeness of the interval. Okay, so for this one, let me just draw another diagram. It's crucial to understand that. If I relax this condition of closeness, let us see what might happen. For example, let me keep one of them filled, A, but let me exclude the point B. Okay? So, and then again, I want to limit myself here on this part. And then what I'm saying, let me draw one very simple graph here. So here, let me just start with this one, okay, and then go up and down. Sorry, let me just go here, and then go here, and then go up to here. But here I am not allowed. Oops, I don't know why this is sometimes working like this. Okay, so let us do it like that, and then I have to exclude this point. So if I ask you, is there any minimum for this function, you will still say might be this is lower. I don't know, this is not a very good picture. Let me clean this to make it more clear. So I will go up and down, and then I will go here, but remember that I have to exclude this point because you see this point is excluded. Okay, so this is the graph of my function. If I ask you, is there any maximum, let me talk about minimum. Is there any minimum for this function? It is not hard to see that this is the lowest point, and it happens at a local extreme point, at a local minimum point. So here, if I ask you what is the minimum of your function, here you see that the minimum of my function is negative because it is below the x-axis, and this is that much, so this is minimum. And it occurs where, let me call this point also alpha, it occurs at alpha. Let me paint the picture a little bit bigger for you. Okay, so now I am asking you about maximum. What can you say about the maximum without me saying something? What is your idea about maximum of this function? Can you tell me what is the maximum, or how can I gain the maximum here in this graph? Okay, so let me tell you. For example, if I say that this is the maximum, do you agree with me? Clearly not, because you say that, okay, this point. Pardon? Do you want to say something?
And maybe you take a point as close to the hollow point as possible.
Okay, so that's a very nice thing to say. But which one is the closest point? Okay, that's a very nice thing that you mentioned. Let us talk about that a little bit. So, for example, let me talk in this way. Please tell me the closest number to 0 and positive. Can you mention any number? So let me just convince you. For example, let me just draw this line. This is the x-axis, and this is the origin, 0. And I am asking you, can you give me the closest possible and positive number to 0? So you might say, let me call this 0.1, for example. You might say 0.1, but 0.1 is definitely not closest. Why? Because I can divide it by 2, yes? I am getting closer. But is this number the lowest? Is this number the closest one? No, because I can divide it again by 2. But is this one the closest one? No, I can divide it by 2. So there is no closest point to 0 from the right hand side, because whatever you tell me, this is the closest. I take your number and divide it by 2, I become even more closer. Is that clear?
Yes.
So exactly like this, if you say this is the highest point, I don't agree with you because I can move a little bit to the right and I increase the height. So this one is higher than this one. So this will rule out this possibility this is maximum. But is this maximum? No, because I can go a little bit closer to B and then I will increase my height. Is this the maximum? This will rule out these two being maximum, but is this maximum? No, because I can continue again and I can go higher. But pardon?
Maybe if you fill that area.
No, the filled area, I'm saying that's the point. I have excluded one point of that one. It means that I am talking now about,
Yeah.
So that's what I'm saying. I'm saying that an interval being closed is crucial for existence of max and minimum. Okay, so if I relax this, I cannot guarantee that there is a maximum or there is a minimum. There might be, for example, here there is a minimum, but I am losing maximum. Is that understandable? I want you to understand intuitively. There is a minimum for this function, but there is no maximum for this function because I can go higher and higher, but I cannot stand exactly on B because B is excluded. So if I ask you what is the maximum, I would say the maximum of f, let me call this function g, the y equals to g of x. I would say the maximum of g does not exist. This I want you to understand. Is that understandable for everyone? So it is crucial to have the endpoints included. Of course, it might happen that I exclude endpoints, but still I have maximum and minimum. For example, let me just draw this picture. Let me just draw it with this tool. For example, I can go from here. So assume that I exclude this one. Okay, this is excluded, this is excluded. Okay, so I am not allowed to fill this point. But what happens? I go here down, I go up, and then I go back here, and then again excluded. So both endpoints are excluded, but do you see that I have a maximum and minimum? This is the highest point, this is the lowest point. I am not saying this is not possible. I am not saying that if you exclude the endpoints, you lose maximum and minimum. No, you might not lose it, but this is the case. If you don't see the graph of the function, you are given a function and an interval which is not closed, there is no guarantee, a priori, there is no guarantee that there is a maximum or a minimum, or both of them, or neither of them for that function, okay? If you want to have a guarantee, so this is one condition that guarantees continuity and closeness, guarantees existence of both max and min for my function. This is, I want you to understand. If you have problems with that, let me answer that. Why continuity, by the way, is important? So far, we talked about closeness was important. It might happen if I relax this condition, I lose one of them, or one of these maximum or minimums, or both of them. But why continuity is important? For example, let me just consider this case. Let me draw another diagram here for you. So for example here, let me think about it myself. So let me keep the interval closed for the time being, because I want to understand what happens if I relax a continuity. Okay, so then I want to restrict myself on this interval, so let me just draw these borders. Okay, and now what happens? For example, I can do something like that. I can keep it this point here, for example. Let me draw it up to here, and then I want to exclude this point, but I will go down. And then I want to work here, and let me, so for example, go up to here. Yeah, let me make it a little bit lower. So for this function, you see what is happening. I am including the endpoints, so they are filled, but I am losing the continuity. You see, my graph is not one piece, it is two pieces. If I ask you, is there any minimum for this graph? You would say still yes, this is the minimum. Let me make it bigger. This height is still minimum for my function. But do you have any maximum for your function? Yes? Do you have any maximum? So for example, is this point the highest point? No, because I can go higher. Is this point higher point? No, I can go higher. Is this point higher? No, I can go even higher. But is there any maximum? Because this point, because of discontinuity, is this excluded, I cannot say that this is the highest point. Because if, let me just tell you, if I go here, if I give this alpha, if I ask you what is f of alpha, you shouldn't say f of alpha is this much, because this is excluded, this is included. So this is your f of alpha. Okay? And then it means that it is clear that I do not have any maximum for the same reason. So you see, I have kept the closeness, but I relax continuity. I lost the maximum point. Okay? Hopefully this is understandable. So what we want to take from this is that if I am facing a continuous function on a closed interval, then this function is guaranteed to have a maximum and a minimum. Yes? Of course, maximum and minimum can occur at different points. For example, if I have this function, it goes up and down and then here, yes, and then it goes up again. So for example, this is not a good picture. I meant to keep them the same. It's better to use Geogebra to show that. I will do that. So for example here, if I go from here to here, you see that maximum and these points are of the same height. I intended to draw the same height. So you see that the maximum exists and occurs at 2 points. It's no problem. But this is guaranteed that if you have a continuous function and a closed interval, that maximum and minimum, you have at least 1 point, the highest, 1 point which is the lowest. Okay, now the question is that if I don't know about the graph of the function and I know only the rule of the function, which is most of the time, how can I find the maximum and minimum of my function? Okay, can any one of you cook up a recipe, an algorithm for that before going to the next page? So if I give you a function, a formula for the function, and if I give you an interval, closed interval, and I guarantee you that this function is continuous, okay? Can you tell me how should I find the maximum and minimum of my function on this interval? But if you understand what is going on, hopefully you can tell what to do. Okay, let me ask you another thing. What are the possible candidate points for maximum and minimum? Can you tell me that?
The local extreme points and the endpoints.
Exactly. Okay, so you know that these max and min happens at two different points: local extreme points within the interval or the endpoints. Okay, now can you tell me how can I continue and find the max and min? Any one of you?
Maybe equate it to 0 and then find the x values.
So this will give you the first candidate, okay? It will give you the local extreme points, the possible candidates for that. Okay, so you are, so now let me just summarize that and go back to go to this page. And this is an algorithm that we actually, I hope that you immediately confirm that this is correct. So what we do f prime, so I am telling you that if you have a function that is continuous on closed interval I, to determine the max and minimum of f on I, you should go through the following steps. I hope that you understand the algorithm. I don't want you to memorize that. First, I determine f prime of x. Why this is necessary? Because by putting f prime of x equals to 0 and finding the answers, I am getting the candidates for the local extreme points. Okay? So I calculate f prime of x, equate it to 0, and solve and find the solutions. And because I am working in this interval, if there is some number coming out which is not in this interval, I throw it away because who cares outside the interval. I only keep those numbers that are in my interval. And then I go and compute the value of f at the points that I found in step 2. But this is not enough because might be these max and min are happening at the endpoints. So I also compute the values of f at the endpoints. And then I get a bunch of numbers in these two steps. The largest value found in these two last steps is definitely the absolute maximum of f on I. And the minimum number that I find, the smallest number that I find in these two steps is the lowest one. As simple as that. So I don't want you to memorize this algorithm. I want you to understand this is the most natural way of finding a max and min of a continuous function on a closed interval. Do you have any questions here? So might be you forget about these steps, but by thinking and imagining a picture of a continuous function on a closed interval, you immediately yourself can come up with this algorithm. Is this algorithm have any problem with any one of you? Please ask me. Otherwise, this is the problems that we want to solve today, and this is type of exam questions. Okay? So now let us start doing this and try to confirm these things using Geogebra. See if Geogebra is available here. So you can see that, yes, but I do not have enough features close to me. I should get rid of my own picture. I don't know how. Okay. So let me, okay, so that's, I think that is enough. So let me adjust everything here. So okay, so you can see that everything seems good. Okay, now let us start solving the problem. You don't have any formula. Of course, this graph is not complicated. This is a parabola. By the way, let me ask you something here. So here might be that's a good idea. Okay, so let us see. My intention was not to put this one first because usually it's pedagogical point of view, it's better to immediately solve the problem here. what can we do? Okay, so let me extend this. Let me solve this problem using this interval first. Okay, so let me write it with black. I will fix it when I want to upload it. Okay, this one, and let me also add another interval which is not closed, like this. Okay, now let me solve this problem number 1 for 2 intervals. Number 1, what should we do? According to this recipe, first I need to calculate my derivative. So my point is that a function is given to you, an interval is given to you, one of them. This is 2 problems, not 1 problem. An interval is given to you, and then you are supposed to find maximum and minimum of your function on that interval. So what we do, the first thing that we do is to differentiate the function. So I take f prime of x, it becomes 2x minus 5. I equate it to 0 and solve it. So this becomes 2x minus 5 is equal to 0. But what I get is 5 over 2. Should I accept it? No, because I have limited myself to this interval between 3 and 6, and 5 over 2 is 2.5, which is not in my interval. So I don't accept it, I don't do anything with that, not in the interval. Okay, so I do not have any points coming from this step. And then, so you see here, determine f prime, solve f prime x equal to 0, and consider only the solutions within intervals, so you don't have that point, and then compute the value of f at the points you got in the previous step. So this is nothing to do with this one because I didn't get any points in the previous step. Compute the values of f at the end points of I. So I will do that. So I have to calculate f, not f prime, f at this end point, which is 3. What is the value? It is 3 to power 2 minus 5 times 3 plus 3. So it becomes 9 plus 3, 12. This becomes minus 3. And what is f of 6? It becomes 6 to power 2 minus 5 times 6 plus 3. So what is the answer here? It is 9, yes? Yes. And then these numbers you put in a box because at the end you want to compare them, yes? So this is one number and that is another number. And then the last step is just comparing the numbers that you put in these boxes. So you see the lowest value that you get is the minimum and the largest value is the maximum, okay? But you need to be a little bit careful if this happens. You see, this point is excluded. For this interval which is closed, don't worry. The highest value that you get, the highest value you get is maximum, the lowest value is the minimum. So I would say that minimum of f is minus 3, maximum of f is 9. Yes? When there is another question, they can ask you what to do to gain this minimum. What to do means that they are interested in the x value. When they say minimum, it means that they are interested in the y value, the lowest y value. When they say maximum, they are interested in the highest y value. When they say when it occurs or what we have to do to achieve this maximum and minimum, they are asking about the x value. So to attain this minimum, x has to be chosen equal to 3. To attain this maximum, x has to be chosen equals to 6. And then it means that these are attained. Okay, so let me just write this, but this was not part of the problem, so let me write it with different color. Occurs, is attained, let me write, is attained when x is equal to 3, and then is attained when x is equal to 6. Is that understandable? But can you tell me what will happen if I look at this interval, which is not closed? Let me tell you again, if it is not closed, it doesn't necessarily mean there are no maximum and minimums, but it might happen this is the case. So can you tell me what will happen?
It will have a maximum but no minimum.
Exactly, because this is why it's important. The minimum is attained when x is equal to 3. Now you are excluding 3. It means that I can get closer and closer to 3, but I cannot stand exactly at 3. So it means that I lose the minimum, but I'm not losing the maximum. So it means that, let me now write it here. So if my interval is now this interval, between 3 excluded, 6 included, this means that minimum of f does not exist, but maximum of f is still 9. Because maximum was attained when x is equal to 6, I haven't touched 6, I have excluded 3, so I am losing this minimum. Is that understandable? Okay, so let me see if we can just draw something with GeoGebra here. If I remember correctly, there should be a feature. Of course, GeoGebra and computers are not good for singling out one particular point, you know. I need to Google around, but I don't think they are capable of just excluding one point, because one point is probably even smaller than 1 pixel, and then if you exclude this, your eyes cannot see that. So if I remember, if you want to put if you just type x squared minus 5x plus 3, which was my function, you see my function was x squared minus 5x plus 3, it will give you the whole graph. But if you want to make it limited, I think you need to start with this instruction, start writing function. You see there is, I am using a Mac, so it might be the keystrokes are a little bit different, but here I type my function x to the 2 minus 2x and then plus 3, and then I use the arrow bottom to the right. I go here, start x value, which was 3 in this case, and then I go to the other one, which was 6 in this case, the final point, yes? And then the graph should be drawn now. Okay, it's here. We don't see it. Let me bring it down. Oh, it's very, so let me make it smaller and smaller so that you can see that. Okay, so this is the graph. And you see that it's not a straight line, because you know that this graph is a parabola, so it's one part of the parabola. And you see that the minimum actually occurs at the end point, so it's a little bit hard to see it probably. Let us first concentrate on the minimum point. So we realize that this point is a minimum point, so let me make it bigger. So you see the minimum value is 6. And that is exactly the answer. Did we got 6? Am I doing something wrong? Because this is not correct. Okay, I typed this wrong. This is not 2x, sorry. This is 5x in the function. I was actually surprised. So in the function that we had, okay, let me show. So do you remember, this is the function, I typed it wrong. So this was x squared minus 5x plus 3. Okay, now let us see what will happen. So you see here the minimum occurs at this end point, and this is exactly minus 3. Let us go back. You see it's confirmed that this is minus 3, the minimum. And then if you go higher, definitely you will see that the maximum is 9. Not more than that, and then it is confirmed here. So the maximum is 9. But of course, even if I actually checked it at home, even if I take this equality by typing the strict inequality, GeoGebra still shows this point. Of course, it's understandable because it's very hard for computers to just exclude one single pixel and then you can see it. I don't know, might be it is singling out one pixel, but we cannot see it. It doesn't make any difference. Okay, so hopefully you agree with me that this is a simple. This is a question. By the way, do you remember this was a parabola? If you remember, this x squared part is positive. What you expect is a minimum. Okay? Do you understand? This is not in contradiction what we learned before. There is a minimum and maximum because I am not looking at the whole parabola. I am just picking one portion of the parabola. Then of course this point is minimum and this point is maximum. I think if you just see, you see, even this is clear in this picture. Minimum is -3 and it is attained when x is equal to 3, yes? And then maximum is 9 and it is attained when x is equal to 6, exactly according to our predictions without having the graph at our disposal, yes? Okay, let us go to more interesting problems. Is there any questions here? Okay, so I think there is no enough space. Let me go to the next page and try to solve this a little bit more non-trivial problem part 2. So let us start doing the recipe. Again, let us consider only this part first, and then using this calculation I can also solve that problem. So this is a function, this is a interval, it is closed interval, and this function is a polynomial function, so definitely it is continuous, so I am guaranteed to have one maximum and one minimum. They might occur at more points than one, but there is a maximum, there is a minimum. What should I do? I need to take the derivative first. It becomes 3x squared plus 10x plus 3. Am I right? Yes. And then I need to put it equal to 0 and solve it. Okay, so how should I solve it? Just using ABC formula is probably the best option here, because if you want to use PQ formula, you need to work with 10 over 3. Okay, so then I will get x is equal to -10 plus or minus the square root of 10 to power 2 minus 4 times 3 times 3 divided by 2 times a, which is 2 times 3. Let me calculate this. It's -10 plus or minus, what is under square root? It is 100 minus 36 divided by 2 times 3 is 6, and then this is -10 plus or minus 10. 100 minus 36 is 64. Square root of 64 is 8 divided by 6, so I will get two numbers. Okay, so one possibility is that x is equal to -10 minus 8 divided by 6 is -3, and the other possibility is -10 plus 8, which is -2 divided by 3 is -1/3. Agree? Okay, but should I accept them? We need to check the interval. The interval is between -4 and 2, so this is acceptable. It is within my interval. This is also acceptable, so I have to keep this and that. So let me put this in boxes. I have to accept both of them. Yes, and then I need to do what? Do you remember the recipe? After doing that, compute this and consider only solutions within the interval. Both of them are in my interval. Compute the value of f at the points you got in this previous step. Compute the value of f at the endpoints and compare them. Okay, so here I calculate the value of f at -3. So what does it mean? It means that I need to go to my function, replace x with -3 everywhere. So this becomes -3 to the 3, and then I have +5 minus 3 to the 2 plus 3 times -3 and then -2. So let me calculate it. It's -27, +45, -9 and -2. So what is the answer? It's 7, yes? Let me double check. So it is 18, 9 and 7, yes. And okay, that's the bad part. I have to calculate f of, so let me put this as in a box. I need it for the future. So this is one of the values that I get. I have to calculate f of minus a third as well. So it becomes minus a third to power 3 plus 5 minus a third to power 2 plus 3 minus a third and minus 2. So it's minus 1 over 27. The other one is positive 5 over 9. The other one is minus 1 minus 2. So if I simplify this, this is just minus 3. So let me take the common denominator to be 27. It is minus 1 plus 15 and minus 81. So what is that? Minus 67 divided by, let me write it below. So it is equal to minus 67. Please correct me if you see there is any flaw in my calculations. Okay, so this is another number. Yes. Okay, and then is it finished? No, because I have to go and calculate the function for the end points, minus 4 and 2. So f of minus 4, I have to calculate again. So it is minus 4 to power 3 plus 5 minus 4 to power 2 plus 3 to minus 4 minus 2. It's minus 64 plus 16 times 5 is 80 minus 12 minus 2. So it is 16. It's 2, yes? 16, 4, 2, yes. So this is another number that I have to put in the box. And finally, f of the last endpoint here, number 2. So it's I have to calculate f of 2. So it is 2 to power 3 plus 5, 2 to power 2 plus 3 times 2 minus 2. So it is 8 minus 20, plus 20, yes? Plus 6 minus 2. So how much is that? 24. So it is 32, yes? Am I right? Yes. So these are the numbers. And I don't think it is hard to see. So these are the numbers in your box. Okay, which one has the highest value? Definitely 32. And which one has the lowest value? Definitely this negative value. Yes? So here, if you ask me what is my maximum, I can immediately answer you that the maximum is 32 and the minimum is what? Is negative 67 over 27. Okay? And then, this is not part of the solution, let me write, is attained when at x equals to, when 32 is attained, 32 is attained when I am choosing x equals to 2. Okay, is attained at when minus this number, I calculated it when it was minus a third, at x equals to minus a third. So it means that the maximum occurs at the right endpoint. This is the right endpoint. But minimum does not occur at any endpoints. It occurs at an internal point, minus a third. Yes? Okay, now, before continuing, can you tell me what happens if I have this situation? So let me make it clear that I am solving this problem for that interval first. Okay, can you tell me what is the answer to this? Assume that in the exam, this was given, this was not given, this was given from the beginning. This is important. You might think, okay, because this is excluded, I don't need to calculate too. Now, you have to calculate. So if in the exam, this was not given, this was given, and this was given, nothing will change up to this point. You have to do everything that I have done so far, but, and of course you can also write these green ones, but because this 2 is excluded, if something happens at 2, you need to rule it out. Okay, so if I want to solve the problem for this case, I would say maximum does not exist because maximum occurs at x equal to 2, it was acceptable in the previous calculation, it is excluded now. So you see, the calculation is exactly the same, the conclusion would be different. So the conclusion is that in that case I do not have any maximum, but still my minimum is this number. Okay, so I didn't have enough space to write it down, so but you understand what's going on. Be careful. If in the exam this and that was only given, nothing will change. The only thing that changes is the conclusion. Calculation is the same. Okay, so let me try to visualize this using GeoGebra. If you have any questions, please let me know. So let me write this down. The function is x to the 3, 5x squared plus 3x minus 2, not to make any mistakes. And the interval is between 4 and 2. Okay? So let us see what we can do with GeoGebra. So these numbers, I can go back and forth. You probably see them. Let us see what will happen here. So let me exclude this and start writing a new function. So if I remember, the instruction was this, so I don't know what happened here, so let me get rid of it, everything, and then start from scratch. So function, I will choose this function, this syntax command. So this becomes x to the 3, and then I go down plus 5x to the 2, and then I go down plus 3x minus 2. So, and then I press this arrow button, it jumps here, the minimum value is minus 4, and then the maximum value is 2, and I have this graph now. Okay, so I don't know if I can fit it here so you can see it. Okay, so first of all, I agree, hopefully you agree that this minimum is here. By the way, there is, I don't know if there is an instruction here called extreme. Let us see if it works or not. I just click here. Okay, so you see these points are extreme points. They are only, this instruction of GeoGebra only shows local extreme points. So okay, so definitely this is a local maximum. You see it here. This is not a maximum, absolute maximum, because there are some points you can see here, they are higher than this one. But this local minimum is exactly the absolute minimum as well. And then this tells you that, so one extreme point occurs at this point. It's minus, I don't know, 333 and then minus 2. So this is the minimum value. This number minus 2.648 should be definitely this number minus 67 over 27 that I got, yes? Let us, by the way, check that. So minus 67, I don't know how should I approximate these numbers using GeoGebra. So divided by 27. Okay, so you see that's exactly that number. You see minus 2.4815 is exactly this number. So what we have done is completely correct according to GeoGebra. And now you see that the minimum occurs in an, and then by the way you see it's minus 0.3333, and that is why, because the minimum occurs when x is equal to minus 1 over 3. Minus 1 over 3 is approximately minus 0.333, yes? So this is exactly, everything is right. But then if I want to zoom out a little bit so that you can see the maximum, what was the maximum value? Do you remember? Oh, it was 32. So this is why we should still go high. Yes? Hopefully you agree with me. Let me see if I can check that. If I can just click here exactly, yes, you see this point is 32. So the highest value of this function is 32. It occurs, you see, it occurs at 2, which is the right end point, but the minimum occurs here. This is the minimum point and occurs within this interval. Okay, is that understandable for everyone? Okay, let me I designed another question. I want to share it with you. So let us see what happens in the next example. Okay, so let us go to the next page. Here I want to solve this problem, number 3. let me make it a little bit bigger for you. So here I design it in a way so you need to be careful a little bit. So first of all, you see that this interval is not closed, so you need to be careful. Might be you are losing something. But you follow the recipe. You don't need to be worried about the interval yet. You just follow the exact recipe. So what I do for number 3, I will take the derivative of my function. It becomes 3x squared minus 6x. I put it equal to 0. Then it means that 3x squared minus 6x is equal to 0. I factor a 3x out. It becomes x minus 2 is equal to 0. So I get two numbers, 0 and what? And 2. Are these numbers acceptable? Yes, because both of them are within this interval. Yeah, so I have to accept them. This one and that one. Okay, now the next step is to calculate the value of f for these numbers that you found and was accepted in the previous step. So I have to calculate f of 0, which is simple. I need to put 0 instead of x. So let me write it if you want to in the future to read it. So the answer becomes 2. So let me put this 2 in the box. I need it for the future. And then I have f of 3. You see, even though 3 is excluded, don't worry about that, just calculate it. It becomes 3 to power 3 minus 3 times 3 to power 2 plus 2, which is again 2. Okay, and then calculate f at the end points. Oh, sorry, what I did, sorry, that was my mistake. I was supposed to calculate first. This is not wrong, but let me keep the order. So here, I want to calculate f for this one and this one. I calculated for this one. I have to calculate for this one first. I was a little bit in a hurry. So this becomes 2 to power 3 minus 3 times 2 to power 2 plus 2. So what's the answer? It's minus 2. Yes. And then I calculate f at the end points. Minus 1 is minus 1 to power 3 minus 3 minus 1 to power 2 plus 2. It's minus 1 minus 3 plus 2. It's minus 2. Yes. And then let me calculate f of 3, which I already did. It becomes 2. Okay. Now I want you to draw the conclusion without me saying something. Is there any maximum for this function? If the answer is yes, what is the value of the maximum and what is the value of the minimum? So I intentionally designed the question that you get the same answers here. So let me ask this question. For the maximum, what is the possible maximum value? If it is going to have a maximum, it should be 2 because minus 2 is smaller than 2. But do you think that this function has a maximum or not? Visualize geometric picture. This value is a maximum value. But do you think it can occur, this function can attain this maximum? What is confusing? No opinion? So I would say, because this value 2 occurs at 2 points. One of them is 0, one of them is 3. Of course 3 is excluded. Yes, So this means that f of 3 doesn't make sense for this function because it's excluded. But I still don't lose the chance of the maximum to be equal to 2 because the same number also is attained for another number within this interval. So in this case, maximum of f exists and it is equal to 2. Yes, because this value of 2, if for example, if it was 1 here, then the maximum value is only this one and it occurs at 3 and 3 was excluded, so I would say that maximum does not exist. But now this value of maximum occurs at 2 different points. One of them is 3, which of course is excluded, but another point is 0, which is included. So again, this is one of those cases, you see, even though this is not a closed interval, but I am not losing my maximum, I am not also losing my minimum. You see, the minimum value is -2. It also occurs at 2 points, 2, which is included, so it's acceptable, -1 again is included. So the minimum value, I didn't have any problem, but I hope that you understand that in this case, this is a coincidental. I was trying to design this idea so that you see this might happen, that this maximum occurs at 2 different numbers, even though one of them is excluded, but still you have the chance of having the maximum at internal point 0. So all of them, I talked about them orally, so that let me don't write this. So maximum of f is what? Is 2, but this is important. If I want to say it is attained, where you are not allowed to say it is attained at x equal to 3, because x equal to 3 is excluded, so you need to write it is attained at x equal to 0. And then if I say what is the minimum of f, you would say the minimum of f is what? -2 attained at x equals to 2 and x equals to -1. Is that understandable? Okay, so let me remember this function. I want to go to Geogebra to confirm that one as well. So we go to Geogebra. Let me clean everything here. We don't need them. And then start fresh. So the function is function. Oh, that was wrong. Sorry. So function, this one. The function is x to the 3 minus 3x to the 2 and then plus 2. And then the initial point was -1. Of course, Geogebra always by default include. I can retype it, but it doesn't matter because you will not be able to see it in the display. So here the other one is 3, and that is your function. So let me make it bigger so that you can see. I don't know why this is. Okay, so let me go and choose this one so that I can move around. So you see, this was the graph. Okay, so here you see between -1 and 3, you see maximum occurs in general here and here. So again, let me use this, if I can do that, extreme points, if it works. No. Yes, so these are the local extreme points. But of course, you see the height of this point, if I can point to that one as well, by manually. So here another point, here is another point. So you see that this point and this point have the same lowest level, and this point and that point have the same highest level. Yes? Even if I exclude this point, still I can attain my maximum, because maximum occurs here and there, and minimum also occurs here and there. So even if you exclude one of these points, you are not losing the minimum, because another point gives you the minimum value. Okay? Is that understandable? Okay, so there is another one. There is no time, and I will continue this. Take this as a homework. I think I have taken this more or less from the book. I want you to think about this problem if you take a screenshot. By the way, these digital PDF files, if you go to the YouTube, because I'm increasing the quality of videos, they are 4Ks now, so for YouTube it takes up to 10 hours to process it. So it will not be immediately available, but when it becomes available in 10 hours or whatever, then below the video you can find the link to this PDF file. But if you just write this down, please, and try to work this out by the next session on Friday, I will first solve this last part, and then I will teach you the last bit of this chapter, which is a very important topic of optimization. Okay? Okay, any questions?